Afternoon, everybody. Welcome to today's webinar, which is hosted by Ricoh 3D and ToffeeX. I'm Mark Dickin, I'm Head of Additive Manufacturing at Ricoh. We're going to be talking to you today about thermal management using advanced manufacturing and generative design. I wanted to point out that the Q&A function is now live throughout the webinar, so please feel free to add anything that you may have as we go along. So on the screen you can see an overview of Ricoh. We're a large Japanese technology company with around 80,000 employees operating in 200 countries across the world. We're probably best known for our photocopier business. However, as you'll learn today, we do lots of other things. We have 242 subsidiaries with core manufacturing in the UK, France, North America, China and Japan. We mainly do our R&D in Japan, but for additive manufacturing and inkjet, we do this in the UK in collaboration with the R&D team. And Ricoh 3D is one subsidiary of Ricoh. Next slide, please. So the topics that we're going to cover today are a quick overview of our vision, a technical overview of the technology and the generative design, and then finish off with a case study. Next slide, please. So the main application that we're directly targeting is thermal management. And to be quite specific, it's heat sinks and heat exchangers, hence the reason for today's webinar. We're currently actively working with automotive, aerospace and the IT sector in a proof of concept phase. And by combining additive manufacturing technology with design software such as ToffeeX, we're having some great success in improving efficiency of batteries, inverters, motors and overall chip performance. We're now going to discuss this in more detail. Next slide, please.
Yeah, that's us now. Hello, everyone. My name is Luca Masi, and I'm heading up the commercial functions of ToffeeX. So what I'm going to do now, I'm going to walk you through what our company does very briefly, so just a couple of slides. And then I'll pass on to my colleague Thomas, which will guide you through the engineering workflow of ToffeeX before going to Ricoh for more information about the binder jetting technology and the case study that we have done together. Now, who we are, ToffeeX, we are a spin-out of Imperial College London, based in London. We have a unique technology. We have developed a generative engineering design software. And in particular, the software is used for topology-optimized thermofluidic components and systems, as you can see in this slide. You can see actually one component we designed to the right of this slide, which is for cooling electronics that has been printed by Ricoh. Now, what do we enable at a very high level? We enable companies to, I would say, go farther, faster. We help them create optimal design for their thermofluid components. We ultimately help them increase the product innovation fast, and ultimately we also help them make more sustainable designs. Next slide, please. Here you can see some of their customers, or at least the ones we can mention. Those are a bunch of companies we work with in the aerospace vertical, such as Boeing, Airbus, GE Aerospace, or research level like Fraunhofer Energy, like Baker Hughes. Automotive, it's a big part of what we do. Examples you see in these slides, Toyota, but we work also with suppliers like Denso and so on and so forth. And we also work with additive manufacturing companies such as Ricoh, US, and more. Next slide, please. And this is where my colleague Thomas will kick in.
Hello, my name is Thomas. I work R&D here at ToffeeX. And I'm going to talk a little bit about ToffeeX, the product, as opposed to ToffeeX, the company. So ToffeeX, the product, is a cloud-based software as a service, computer-aided engineering tool. And it should look familiar to anyone who's ever used any sort of computer-aided engineering tool before. The general workflow is to start with an empty space, a design domain, a blank sheet. And then using our design tools, users can generate optimal designs for their components. So you start from an empty space like this, and with some geometry manipulations and labeling, you can set up essentially your geometric representation of your design space. And then moving on from here, the next slides, you start to set up your optimization and design problem. Now this involves many steps which will be familiar to anyone who's worked with computer-aided engineering tools. So there's a mesh generation stage to discretize your space. And there's also a simulation setup where in this case, a CFD problem is set up specifying inlet flow rates, boundary conditions at walls and outlets, temperatures and heat sources associated with the various chips that in this case are trying to be cooled down. And then on top of setting up your simulation problem, the real magic of ToffeeX is to also set up an optimization or design problem. And this is where the user tells the software essentially what they're trying to achieve with their components. And in this specific example that we're showing here, you can see there's an inlet coming in at the top, and at the bottom of the design domain, there is a heat source. And so you've got flow coming in and then coming out the sides of the cylinder. And what we're trying to achieve is to cool the heat source as much as possible with the incoming flow rate, and then also try to minimize any losses that we experience from pumping the fluid through the system. And so that's what we're setting up here. And on the next slides, you can see an animation of the optimization process. So this is accelerated probably quite a lot. I imagine something like this might take 2 or 3 hours with ToffeeX. But what you can see here is essentially the white or the gray area is the solid parts of the component that is being calculated by ToffeeX. And then you can see the flow distribution through the system. And essentially all that's happening here is creating a series of impinging jets on the heat source, and then using these impinging jets to cool the heat source as much as possible. So if we go to the next slide. So it's not just enough to generate one design. We think this is very important. What's more valuable than generating one design is generating many designs. And what's even more valuable than generating many designs is understanding many designs. So users can explore design spaces by specifying different weightings for their objectives, exploring different constraints on the design, whether it's manufacturing or weight or otherwise. And then through generation of many designs, they are able to select the best design for them. So this is just a simple example where 3 different designs have been generated by ToffeeX, each of them favoring different aspects. So you have sort of like design 1, which is the compromise design, and design 2, if you want a really low pressure drop, or design 3, if your heat transfer is your most important consideration. Go to the next one. And then finally, just a word about other considerations, especially manufacturability. So from the beginning, we were desperate here at ToffeeX not to just be an academic pretty picture generator. We care about real world engineering considerations. One of these, of course, is the ability to manufacture your components. Built into ToffeeX are several constraints on the optimization and design process, which ensure manufacturability using several different manufacturing techniques, from traditional stamping processes, for example, to additive manufacturing, such as Ricoh's metal binder jetting. So I think we go to the next one there.
Right. Hi guys, I'm Issei Song. I'm metal binder jetting expert in Ricoh. And from me, I have give some explanation about our binder jetting process. So binder jetting is one of the additive manufacturing process, uses inkjet head, which is our Ricoh's core technology. And the process starts from importing 3D models to printer. And when the print starts, the printer makes powder layer with recoating roller. Once powder layer is created, the inkjet heads deposit binder on it, and by repeating these, the 3D geometry will be printed. And after printing process, the binder is still wet, so the build box will be sent to drying oven for curing, and this process will take up to 1 day. After the drying process, the build box is sent to nitrogen inert depowdering station for depowdering safely, and we can get the green parts. The surrounding powder will be sieved and can be 100% reused. Finally, the green parts came out from build box are sent to furnace for debinding and sintering process. And these two processes also takes 1 day. And you can get one batch of final parts within about 1 week. And on the photo on the right side, you can see our pilot plant in Telford, UK. And with the facilities, we can do some sample working activity with our customers in Europe. Please go next one, please. Yeah, and this slide visualizes our core capabilities. So the technology development is focused around the material, which is powder, alloy, and binder composition, the design of AM, and that is through our software and know-how. And then the process, the mainly sintering, which is the most challenging aspect. Yeah, next one, please. Yeah. And for material, we designed aluminum alloy powder and binder to optimize the printing process. And generally, the sintering of aluminum is not common because the oxide layer inhibits the sintering process and it makes the process tricky. So with a combination of Ricoh's aluminum alloy powder and the controlled liquid sintering process, we enabled the sintering of aluminum. Also, the depowdering process is another hassle in binder jetting technology. So as you can see in the videos, with this unique wet depowdering process, it can help the creation of some complex inner structures. So with our technologies, we can print aluminum parts with a fine structure, and this is ideal for thermal management applications such as heat sink or heat exchangers. Next slide, please. And for the material property, currently we have aluminum silicon alloy, and we use this for sample working. The density of printed parts is up to 98%, and the heat conductivity is around 190 watts per meter Kelvin. For the parts geometry, the minimum thickness of wall, we can achieve 0.3 millimeters, and also we can try thinner, but this is highly depending on the aspect ratio of parts. Let's go next one. And finally, the design is another core of our capabilities. Next, please. And we have two types of design approach. The design for AM, we call DFAM. This is to improve the performance. And we can support customers' parts design by applying some special structure or topology optimization. And this is why we collaborate with ToffeeX. And another approach is the modification for AM, we call MFAM. And while binder jetting has the advantage of high productivity, it has the difficulty of causing deformation during sintering process. So we will provide some advice based on our tools and know-how to modify the model shape and get the desired function. I will pass to Enrico.
Thanks, Insei. Thanks for the introduction about the technology. I'm Enrico Gallino. I'm one of the senior engineers here in the Ricoh 3D team. And I would like now just to do a bit of a deep dive into a specific case study. In this particular case, we're going to look at an heat sink for an inverter used in an electric vehicle. And one of the key challenges when we deal with inverters is the fact that they generate significant heat during operation. So having an effective thermal management is essential to maintain efficiency and reliability, especially when the inverter is working at elevated power density. So a traditional solution like the one you can see here on the left-hand side of this slide that generally involves the use of pin-fin cold plates and using copper as the material of choice to make them. However, this type of solution have limitation in terms of heat transfer, pressure drop, and in particular weight, which is a very critical factor for any transportation application. So when we combine our binder jetting technology and printing aluminum with the advanced design capabilities of the ToffeeX software, we can achieve some pretty impressive results. Move to the next slide, please. So from a design perspective, using the ToffeeX software, we are able to generate very quickly, just within hours, several design variations for the core of the cold plate. And in this particular case, the design was optimized in order to minimize the pressure losses and maximize the thermal dissipation of the component, but also taking into account the constraint in terms of design space, the material properties, and also the constraint of the manufacturing process. So as you can see on the right-hand side of this slide, the design generated by the software has a much more organic structure compared to the traditional pin-fin design. It's quite complex, and you can see that the surface area is maximized. The design also introduced much more complexity in terms of the fluid pathways, and this in turn enhanced the turbulence quite significantly, which in turn it ultimately boosts the heat transfer during the operation. And based on the different design generated by the software, as Thomas was mentioning before, the software will give you a few design options. We picked the one with the best balance in terms of performance metrics. If you move to the next slide, please. So from this design, we then produced a physical component of the selected design, and we tested it in the real world and compared the performance to the one of the pin-fin copper component. And as you can see on the graph here, the optimized design allows to achieve a significant reduction in thermal resistance, about 7%, which is pretty impressive considering that the copper has a thermal conductivity which is almost the double of the one for aluminum. The weight was also significantly lower, thanks also to the lower density of aluminum compared to copper. And also the results obtained by the real world test, they were really close to the simulation results provided by the ToffeeX software, which further confirmed that the effectiveness of the optimization model used by the software. And one particular thing for the component we produce is that it was manufactured using an hybrid approach, where the central core part of the component was produced using our metal binder jetting technology, whereas the base plate was used conventionally manufacturing method. In this case, was machined, and then the two the different sections were joined together by a diffusion bonding method that we developed, and pass it over to Insei that will provide more details on this.
Yeah, thank you, Enrico. So as he mentioned, we have used our joining process to produce this inverter heat sink. And let me give some additional information about this. And next slide, please. Yeah, so taking advantages of our aluminum alloy powder, we have developed a post-process to join 3D printed parts with some metal parts of conventional method. And generally, the 3D printed parts are very expensive, but with this process, we could reduce the manufacturing cost. The joining process is very simple, so we do not use any brazing paste or flux, but just put the two parts together and do some additional heat treatment. So in the case study of inverter heatsink, we have printed the fins and joined them with covers and base plate made by conventional method. And this joining not only reduces parts cost, but also enables the creation of large parts, which could not be sintered before. And please go next slide. Yeah, this graph is showing a sense of parts manufacturing cost. So you can see the cost of binder jetting is much cheaper than PBF, powder bed fusion, but it's still more expensive than the forging process. But by using the disjoining technology, we could reduce the usage of 3D print powder material, which is one of the most expensive factors in manufacturing. And we could achieve the same, almost same cost as a conventional method.
Well, thank you. Thanks everybody for attending. We'll send out the recording and have a good rest of your day.
Thank you.
Bye-bye.
Bye-bye.
Bye.
Bye.